Hi guys, it's Miss Townsend here. I just wanted to make a video for you over quiz number 4. So this is our first quiz that covers any calculus, really. We're dealing with vector valued functions and what they look like. We're graphing them in the plane and in space. We're also differentiating, anti-differentiating, and anti-differentiating these functions. Computing their limits, and that's going to require some prerequisite material. My plan for this video is to go through the key for the Monday, Wednesday version of this quiz. The Tuesday, Thursday version of the quiz was very similar. You just had two different functions on the first page, but the ideas are exactly the same. So this video is for you if you decide to reassess over this material. The questions are not going to be identical. I'm not going to give you the same problem with just a different function, although I very well could do that a little bit. You just need to be prepared for all of the variations on the theme. And for this first standard V8, which is about paths in the plane and in space, we need to know how to graph these functions, we need to know how to find their domains, and we also need to know how to compute limits of these functions. So that's going to require some prerequisite content from pre-calculus, where we find domains. We also need to know how to graph functions in 2D, and also a little bit in 3D. And that's going to require some prerequisite material from the previous chapter. And then limits are something that are easy to calculate in Calc 3 if you remember how Calc 1 limits behave. But if you've forgotten some things about Calc 1 limits, you might have trouble with limits of vector valued functions. So I'm going to go through V8, and if the video isn't too long, I'll do the rest of the key as well. I might make two separate videos, one for V8 and one for V9, but I just wanted to show you how to solve these problems or similar problems, just in case you decide to reassess, and also so that you can have not just my written key, but a video of me talking through the key, so that you can learn from your mistakes when I hand your quizzes back next week. Okay, so we've got a vector valued function. It's in the plane. It has two components, x of t and y of t. And we're told that the x component is negative square root of t, and the y component is 4t minus 1. So we're asked to sketch this path given by this function by eliminating the parameter t. If you took Calculus 2 at TCC last semester, you've eliminated the parameter t before. What we're doing here is we're going to set x equal to negative square root of t, because that's how it's defined. That's my x, and then that's my y, so I'm going to write that down as well. Y is 4t minus 1. And when we're eliminating the parameter t, all that means is that we are putting these two equations together in such a way that there are no t's. I just have an equation involving x and y. We call that the rectangular equation. So how we generally do that is we take one of these equations and solve it for t, and then substitute into the other one. Now we could solve this one for t because it already has a t to the first, but I think it's a little bit simpler to solve this one for t and then substitute it in over here. I'm going to choose to do that. I also would say it's simpler to do that because I'm used to y being some constant times a function of x minus a constant. Like, that's very comfortable for all of us from our studies of pre-calculus. I could get x as a function of y, but we're not as familiar with that or comfortable with those types of functions. It's a little bit harder to graph. So we're going to get t in terms of x and then substitute, rather than getting t in terms of y and then substituting. So I'm trying to get t by itself here. First, I'll multiply both sides by negative 1. And then to get rid of the square root, I'm undoing that by squaring both sides. Now this is not negative x or it's not negative x squared, it's negative x squared. So that's negative x times negative x. That's positive, two negatives multiplied to give us a positive. So I've got x squared there equals square root of t squared is t, as long as t is positive. Now there's one other restriction that I should write down. X is a negative square root. Square roots are always positive except for when they're 0. If I multiply that by -1, this is always negative except for when it's 0. Because the square root's always going to return a positive number or 0, and then I multiply it by -1. So it's going to return a negative number or 0. So what does that mean? That means our x value has to be less than or equal to 0. But provided x is less than or equal to 0, x squared is equal to t. So I'm going to keep that in mind. X squared is t. Those are the same thing. And I'm going to replace this t with x squared. According to that equation, I can do that. So I have y equals 4 times whatever t was in terms of x, which happens to be x squared, minus 1. And don't forget that restriction, x is less than or equal to 0. So this is called the rectangular equation of our curve, as opposed to these which are called parametric equations. And hopefully you look at that and you say, oh, that's just a parabola. Yes, you're absolutely right. That's a parabola, but we only get one part of the parabola. We get the part of the parabola where x is less than or equal to 0. So I notice when x is 0, y is going to be -1. And then because x squared is always non-negative, the y values are always going to be larger than -1. So keeping that in mind, I'm not going to draw my x and y axes with the origin here in the middle. I'm just going to draw them down here because I think that makes the most sense. I don't need x to be positive anywhere, so I don't really need quadrant 1. So there's my y-axis, there's my positive x-axis. X is negative here. We just want to sketch this. So I'm going to use just one little box as one unit in the y direction. So that's -1, positive 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and so on. Okay. Now over here in the x direction, because I've taken my y equals x squared and I've multiplied it by 4, that's stretching everything by a factor of 4. That's going to make it really tall and skinny, if you remember from pre-calculus. I don't want it to be that tall and skinny on my paper. I've got all of this room. So I'm just going to spread out my x values a little bit over here. You don't have to do this for your graph to be right. It's just going to make it a little bit easier for us to see. So I think I'm going to use like 3 boxes to equal 1 unit in the x direction. So that's -1 for x, -2 for x, -3 for x, -4 for x, and so on. Okay. Now, we were supposed to sketch the path using this. So we can choose different x values that are less than or equal to 0 and find the corresponding y values. That's one way of doing it. Or we can create a table of values. I highly recommend making a table of values that includes the parameter t, just so that it's obvious to you whenever you get like square roots of a negative number, and so x would be undefined, things like that. So I'm going to make a little table. So here's t. Here's x of t equals negative square root of t. So y of t equals 4t minus 1. And we're just going to fill in the table. Now because x is this square root, and we can't take the square root of a negative number, t has to be greater than or equal to 0. So I'm going to substitute t equals 1, and maybe, because we're taking square roots over here, or I said t equals 1, I wrote t equals 0, sorry. T equals 0, t equals 1. And I could put t equals 2, t equals 3, t equals 4, and so on, but I'm about to take a square root. So I'm just going to use perfect squares for t. Let's use t equals 4 and 9. And I think 16 would be too large for our y, so I'm not going to worry about that. Okay, so I'm going to use these t values. I'm going to substitute them in here for x and substitute them in here for y. So y, or x, is negative square root of 0. Square root of 0 is 0. Opposite of 0 is 0. Negative square root of 1 is negative 1. Negative square root of 4 is negative 2. Negative square root of 9 is negative 3. And y is 4 times t minus 1. And I'm replacing t with 0, 1, 4, and 9. So I get negative 1, 4 minus 1 is 3, 16 minus 1 is 15, 36 minus 1 is 35. Now, y equals 35 is not on my graph, so I'm not going to use that point. I think I'm going to use these points. Now, when we're plotting over here, there's no t-axis. So you're just going to plot the x and the y that goes with it that happens to be associated with t equals 0. So I can think of this as my x position and my y position in terms of time. So at a particular time, we're at this location, x equals 0 and y equals negative 1. And at time t equals 1, we're at this location, negative 1, 3. And t equals 4, we're at this location, negative 2, 15. And t equals 9, we're at this location, negative 3, 35. Obviously, that's not going to go on my graph. Okay, so I plot 0, negative 1, and then negative 1, 3, and negative 2, 15. And that's all I get, because the next one would be negative 3, 35, and that's way off the page. And this is t equals 0, we're at this location, and at t equals 1, we're at that location, and at t equals 4, we're at this location. So as t increases, we're going this way along the path. Another way of inferring orientation is to just think of limits. As t increases, as t goes to infinity, what happens to x? Well, it's a positive number times a negative 1, so x is going to go to negative infinity as t increases. So x decreases as t increases. Also, as t increases, y increases. So as t increases, y is going up and x is going down. So we're going this way along our path. Okay. All right. Now, when we're asked to sketch r prime of 1 at the point of tangency, that means we have to figure out what the point of tangency is. The point of tangency for r prime of 1 is the terminal point of r of 1. So we're just looking at x of 1, y of 1. When t is 1, x is negative 1 and y is 3. So we are at this point, that's r of 1, it's a vector that starts, at the origin and points to that location. But we weren't asked to sketch r of 1, we were asked to sketch r prime of 1. So we're going to sketch r prime of 1 with its initial point at negative 1, 3, and it should be tangent to the curve. In order to do that, I need to compute the derivative of this. So I'm going to write r of t over again. R of t is negative square root of t. Now remember, that's an implied 1 and an implied 2, so that's a t to the 1/2 power. And then we have a 4t minus 1 over here. When we take the derivative of that, we're just using the power rule. Bring the power down, bring the negative down, then bring the power down, then multiply by t to the 1 less power. And we get that. And I run out of space. I'm going to use a little bit of this space down here. So r prime of 1 Well, that's this. That's negative 1 over 2 times the square root of t times I hat plus 4 times j hat. And I'm replacing the t with a 1. So r prime of 1 is the vector that starts at some point and goes negative 1/2 unit in the x direction and 4 units in the y direction. So we're starting at x of 1, y of 1. We're starting at this location, the terminal point of r of 1. We go 1/2 a unit in the x direction and 4 units up in the y direction. So that was y equals 3. We want to go up to y equals 7. So we're going from 3 to 7, that's 4 units. So go 1/2 a unit this way, up 4 units that way. And that's r prime of 1. Now it doesn't look exactly tangent to the curve. It looks like it's a little bit off. It looks like the curve is a little bit steeper, but that's just because my graph isn't perfect. That's okay, we do the best that we can. Alright, so we've sketched the curve, we've eliminated the parameter, we've found r prime by computing the derivative of r and then substituting t equals 1. And then we sketched r prime at 1, or r prime at 1, with its initial point at x of 1, y of 1. So we can see that that's our tangent vector, or our velocity vector at t equals 1, points in the direction we're going, and it's tangent to the curve. Okay. Now you're asked to sketch a path that has 3 components, x of t, y of t, and z of t, given by this. And we're going to eliminate the parameter t. So we're doing actually something very similar to what we did up here, but in this case, because we've got cosine of t and sine of t, it makes more sense to get rid of these trig functions, cosine and sine, using the Pythagorean identity. Sine squared plus cosine squared is 1 as long as the angles are the same. So that's what we'll do here in order to eliminate the parameter t. Now, as we talked about in class, when I eliminate the parameter t, I'm not going to get a curve, I'm going to get a surface. I'm going to get a surface involving x, y, and z, and it's going to be one of those surfaces that we talked about in the previous chapter. Now, that surface itself is not the path. The path is a one-dimensional object that lives in 3-dimensional space. It's a curve that's being traced out as t increases. So when we eliminate the parameter t, we're going to get a surface. The curve is going to lie on that surface. That's why it says here, the curve lies on a familiar surface from the last chapter. Use that surface to help guide you in your sketch. So we're going to eliminate the parameter t to find the surface, and then we're going to think about what happens as t increases along that surface. Whenever we see cosine and sine, remember we think about a spiral. It's like we're going around the unit circle, but now we're multiplying it by the square root of t. And meanwhile, as t increases, y is increasing. So we've got to think about how all of those factors come into play when we're graphing this function in 3D. Okay, so let's talk about eliminating the parameter t. In order to do that, first I identify x, y, and z. And rather than writing x of t, y of t, and z of t, I think we're going to say it's implied by context that x, y, and z depend on t. So we're going to write it this way without the of t part. X equals this, y equals this, and z equals this. And we'll solve for cosine. And we'll solve for sine. And you might say, Miss Townsend, why are you doing that? The reason we're doing that is that's what we always do whenever we see a sine and a cosine in our parametric equations. And the reason we always do that is because we can use the fact that sine squared plus cosine squared is 1 to get rid of these trig functions. So we're going to get cosine by itself by dividing both sides by 2 times the square root of t. And get sine by itself. So I've got z equals, or z divided by 2 times the square root of t equals sine of t. And now I have equations that are for sine and cosine. Well, we know from trig that sine squared plus cosine squared is 1. So we're going to put those two pieces together. We've got sine squared of an angle plus cosine squared of the same angle equals 1. And I'm going to replace my sine of the angle, which in this case is t, with z over 2 times the square root of t. Just substituting this in for sine of a. Just using a for angle, just trying to make it generic. And cosine of a is, well, in our case a is t, so cosine of t is x over 2 times the square root of t. Now, this equation does not eliminate t. We still have t's in it. But we're closer to eliminating t, because now I have an equation that relates x and z to each other. Excuse me. So I've got this equation with an x and a z in it, and it doesn't have those trig functions anymore. So we'll square this. We're going to simplify everything. Square the numerator, square the denominator. You've got 2 factors in the denominator. Whenever you've got a product of 2 factors and you're squaring them, you just square each factor separately. So I have 2 squared is 4, square root of t squared is t. This is also going to be a 4t. And then let's multiply both sides by 4t, and I like to put my x's first, just alphabetical. All right. Now this does not eliminate the parameter t, but we're close. We've got a 4t by itself over here, and x squared plus z squared here. And we'd like to write this entirely in terms of x, y, and z, but I've got this t in it. Well, look over here. This is a very good thing. Turns out that y is equal to 4t, so that's exactly what y is. When we're on our curve, that's our y. Okay, so we've got this equation of a surface. Y is raised to the first power. X and z are both squared and they have the same sign, and they're both positive. We're not adding or subtracting anything. So this is an elliptic paraboloid. We know that from our previous studies of quadric surfaces, and it opens on the positive y-axis. Now don't be misled here. We're looking for a curve, not a surface. But this surface is going to guide us because our curve satisfies, or x of t, y of t, and z of t satisfy this equation. So that curve lies on this surface. So I'm going to say the curve generated by r of t lies on this surface. And it's an elliptic paraboloid with symmetry on the y-axis in the y direction, and because the y is raised to the first and these guys are positive, it's going to open around the y-axis. So it's going to look roughly like this. I'm used to z being x squared plus y squared. It's a little harder to draw y equals x squared plus z squared, but that's the idea. And I'm not done yet. I have to think about what happens as t increases. What does our curve look like that lies on this surface? Well, let's figure it out. When t equals 0, I'm going to be at a certain location. Remember, these are the coordinates, the x, the y, and the z, for every t value, which is a time. You can think of that as when t equals 0, at time t equals 0, we're at this particular location, the location given by the terminal point of this vector valued function. So at time t equals 0, x is 0, because square root of 0 is 0, y is 0, so 4 times 0 is 0, and of course square root of 0 is still 0, so z is 0. So I get 0, 0, 0, so we're right here at t equals 0. Now at t equals, let's say, pi over 2. And you don't have to make this chart, but you can if you want to. And I'm not going to write the equations, although I usually like to just give myself a visual reminder of what x, y, and z are in terms of t, but I've run out of space, so I'm just going to write it like this. When t is 0, x, y, and z are 0, So we are located at the point x of t, y of t, z of t is 0, 0, 0. Now we've got trig functions, so I'm going to substitute in multiples of pi over 2 or pi over 4, something that's easy to evaluate with our trig functions. Here, I've got x equals 2 times the square root of pi over 2, if I'm at this t value, t equals pi over 2, and I'm multiplying by cosine of pi over 2. Now, if you don't remember, it's okay, but remember how cosine behaves. It looks like this, and all of the interesting things happen at 1/4 of the period. So that's pi over 2. When I say interesting things, I mean mins, maxes, and zeros. So it starts at its max, 1/4 of the period later at pi over 2, it's equal to 0. So I've got 2 times some positive number times cosine of pi over 2, which is 0. And then I've got 4 times pi over 2. So 4 times half of pi is going to be 2 pi. And sine of pi over 2 is 1, because this is what sine looks like. So I get 2 times square root of pi over 2 for my z value. So we're at this location, 0, 2 pi, and 2 times the square root of pi over 2. Now, just to see what's going to happen, let's plug in pi. At pi, we get 2 times square root of pi times cosine of pi, which is -1. So this is -2 square root of pi. Y is going to be 4 pi. And sine of pi is 0. So we're at this location. Now remember, the whole time we're on this surface, question is, what are we doing on the surface? Are we just like scribbling back and forth? I don't think so, but let's see. All right, we start at 0, 0, 0, and then pi over 2 radians later, x is still 0, but y is 2 pi, and z has the value of 2 times the square root of pi over 2. It's a positive number, so y is 2 pi and z is that number, so I think we're right here on the surface. It's t equals pi over 2, and that's a point in the xy, or excuse me, the yz plane. It's literally that point right there. And then at t equals pi, x is negative. This is the positive x-axis, so the x-axis is going sort of into the page, it's going behind us, and x is 2 times the square root of pi. At this point, y is 4 pi, and z is 0. So we're going to be on the other side of the surface. I think we're oscillating, not oscillating, but we're like spiraling around the outside of this surface. And as we spiral, because of this cosine of t and sine of t, we're seeing that spiral behavior. The x-coordinate, it's being multiplied by this number, this factor that's always between -1 and 1. But this amplitude, or what we think of traditionally as an amplitude, the function in front of the cosine of t, like that's increasing. So as t increases, we go around and around, and the x values, the magnitudes increase. So we're getting farther and farther from y equals 0, z equals 0. That's where x is 0. I hope that makes sense to you. So what ends up happening is we end up with something like this. Of course, this is not to scale, and I'm probably making it look like sort of twisted. It's supposed to all be like, I would say, perpendicular to the y-axis. I'm not doing a very good job of indicating that. But that's the idea. I'm on a curve that's on this surface, and we're going around and around and around. And as t increases, this number multiplying these trig functions is increasing, so we're getting farther and farther from that -1 to 1 that we started on. And then y is increasing the whole time, so we're going farther to the right. Okay, so that is how we sketch this vector valued function on the surface. Now this question is almost an algebra question. It's asking us how we find the domain of a vector valued function. And then it asks, what values of t do we need to exclude? Well, if r of t is defined to be x of t, y of t, z of t, the domain is a set of all t in the real number system, in the reals, for which x, y, and z are all well defined. So I need the t values for this, the t in the domain for r, to be in the domain of x, y, and z. Because I have to be able to plug that t into every component here. So it turns out if r is a vector valued function with these components, the domain of r of t is just the set of t values where the domain of x of t, y of t, and z of t, or the set of t values that the domain of x of t, y of t, and z of t all have in common. That set of z values, or t values that they all have in common, is called the intersection of those intervals. So I'll find the domain of x of t, and I'll intersect it with the domain of y of t, and I will intersect that with the domain of z of t. So I basically have to solve 3 pre-calculus problems and then do, I wouldn't say high school algebra, a pre-algebra problem where I'm just finding the intersection of these sets. The question says, how do we find, or what values of t do we need to exclude? Well, remember, whenever we have a function of t that's just given by an equation, there's always an implied domain. We want to include all real values of t except those that cause 3 problems. So I'll say include all real numbers t except those that cause the following problems. Division by 0 is one of them. We have no desire to divide by 0. Doesn't make sense to take something and divide it into 0 pieces, so we're not going to do it. We also don't want to take even roots, so usually square roots, but sometimes 4th roots, 6th roots, and so on, of negative numbers. So those are well-known numbers. They're complex numbers, but these are real valued, or x of t, y of t, and z of t are real valued functions. We only want to put real numbers in, and we want real values to come out. So we don't want any even roots of negative numbers, because then we'd have complex numbers. We'd have i's in our answer, and we don't want that. So we want to include all real numbers t except those that cause division by 0, even roots of negative numbers. I'm going to say, is it and or or? Or. We don't want to take logarithms of negative numbers or 0. Turns out logs of negative numbers are complex numbers. And it's not going to work in this class because we're dealing with functions of real variables that have either real values or map to points in Rn. Each of the components is a real number. Okay, so let's look at the rest of this. Now I've got R of t. It has 3 components, x of t, y of t, and z of t, and we're asked to find the domain. So the first thing I need to do is I need to find the domain of these 3 guys, x of t, y of t, and z of t. And I have to remember that when I do that, I have to exclude any t that cause division by 0, even roots of negative numbers, and logs of negative numbers are 0. So I'm going to find the domain of x of t first. Now please write this down, guys. As you're doing your quiz, label your work so that anyone who reads after you can read what you've stated as a complete sentence. Don't just write t minus 4 is not equal to 0. T is not equal to 4. That's true, but I'm trying to find the domain of x of t. The domain of x of t is a set of real numbers. So I'm going to write this in set builder notation. This is the set of all real numbers t, and this little bar is read such that everything after the bar is true. Well, if I've got division in my component, I know I can't divide by 0, so I set anything that's in the denominator that could potentially be 0 not equal to 0. So I want all real numbers t except, or such that t minus 4, the expression in the denominator, is not equal to 0. And that's because we can't divide by 0. So if you have a denominator, set whatever's in it not equal to 0 and then solve for t. I rearrange this equation. This is saying if I solve this for t, I have t is not equal to 4. So I want all real numbers t such that t is not equal to 4. On the number line, that's everything from negative infinity to 4 and 4 to infinity. You do not have to draw this, but for some students it still helps. I'm excluding 4, so I put a big old circle around it. And I want all the numbers that are not equal to 4 to the left and to the right. Now this is a number line of all real numbers. It goes from negative infinity to infinity. Now that's a concept. It's not included. I never use brackets on the infinities. So I'm going all the way out to the far left. The x's, or the t values, are getting smaller and smaller and smaller and smaller. Larger in magnitude, but more negative. And then on this side, the t values are getting larger and larger. Truly larger in magnitude and positive. So we've got this. Okay, now we're going to do the same thing for y of t. This is the set of, the domain is the set of all real numbers t such that, now look at this one, I've got a square root. We can't divide by 0, no danger of that, there's no division here. I can't take an even root of a negative number. Oh, I have an even root, I've got a square root. So this expression under the square root cannot be negative. It's okay if it's 0, we can take the square root of 0, and we can take the square root of any positive number. So whenever you have an even root in your problem, you're going to take the expression under that root, and you're going to set it to be greater than or equal to 0. Because we can take the square root of a positive number. We can take the square root of 0. Totally fine. And then you're going to rearrange this inequality. So our domain is a set of all real numbers t such that this is true. Get t by itself by adding t to both sides, then maybe rearranging. 9 is greater than or equal to t, which means t is less than or equal to 9. And in interval notation, that's negative infinity to 9 inclusive. Now if you're not sure, you can always draw a number line. T can equal 9, so I want to include that. And it can be less than 9. Since it's less than, we shade to the left. When I write my intervals in interval notation, I read from left to right. I know for some of you, you might be yawning, you might say, I absolutely don't need that. I know, but there are some people in class that do need it, so I'm showing this for them. Some people are visual people, and that's going to be helpful. Okay. Now for domain of z of t, we're looking for all real numbers t such that we don't divide by 0, we don't take even roots of negative numbers, and we don't take negatives of, or logarithms of negative numbers or 0. That's a logarithm. I'm not in danger of dividing by 0 like I was with x, and I'm not in danger of taking an even root of a negative number like I was with y, but with z, I've got a logarithm. The expression inside the logarithm, which is called the argument, it happens to be t. That can't be 0, and it can't be negative. If it can't be 0 or negative, it has to be positive, because I can take the log of a positive number. And there's nothing to solve there. T is already by itself, so that's the interval from 0 to infinity. So there's a 4 and there's a 9, and I'm trying to keep those roughly in order. So when I draw this on the number line, I need 0 to be to the left of 4. So I'm going to start at 0 and go to infinity. Okay. Now that is not our answer. We're trying to find the domain of R of t. So I need the t values that are in all 3 of these sets at the same time. So the domain of R of t equals the domain of x intersected with the domain of y intersected with the domain of z. And you could write all those down, but I've written them up here. I think I'm just going to do the intersection just by looking at these intervals. I'm looking for where these 3 sets overlap. So let's look. We're looking from left to right. All these t's are in both of these sets, but they're not in this one. So it looks like we don't get any t's in common until t equals 0. And then even at t equals 0, that's not going to work because t equals 0 is not in this set. So there's sort of a dividing line there. But look, all the t values between 0 and 4 are in that set, and that set. So we're going to go from 0 to 4. T equals 0 is not included because it's not in this set. T equals 4 is not included because it's not in that set. And then we keep going. Where's the next natural dividing spot? I hope you said t equals 9. Now all these t values are in all 3 sets, including t equals 9. So we're going to go from 4 to 9. Since 9 is in all 3 sets, we include it. That means we use a bracket. Now 9.1, anything greater than that, is not in the domain of y of t. If it's not in the domain of y of t, let's say 10, I can plug in 10 here, but then I have the square root of 9 minus 10, square root of negative 1. That's I. I don't want I. Not in this class. So those t values are not in all 3 of these domains, so those are excluded. So we want all the t in this set and this set, or all the t in this interval and this interval. If we're talking about t's in both intervals, we put a union between them. Okay, so that is our domain. And then this one says, find the intervals over which R of t is smooth. Now R of t is smooth whenever x prime, y prime, and z prime are not all 0 at the same time. So I'm going to write R of t down. And I'm going to write it in such a way to prepare for differentiation. That's R of t. And I don't know why I put an extra little 3 over there. That 3 in the denominator doesn't belong. Put a little white out there so that when I scan this and send it to you, you don't have to see that ugly 3. All right, so this is our R of t. Now remember, R of t is smooth, and the curve generated by R of t is smooth. When you take the derivative of this, and that vector r prime of t is not equal to the 0 vector. So x prime, y prime, and z prime aren't 0 at the same time. Now before I differentiate, I'm going to simplify. As long as t is not equal to 4, and remember t is not equal to 4 because t equals 4 is not in our domain, x of t is just 3. So we get 3 and this over here. Now you don't have to show that all 3 of these are non-zero at the same time. If you can show one of them as never 0, that would be enough to show that R of t is smooth on its domain, one of the components of R prime. But because of the way it's defined, I'm just going to compute R prime this time. So this is R on its domain. That's what it's equal to. So R prime of t is equal to the derivative of each of these components. Derivative of 3 is 0. Derivative of something to the 1/2 is 1/2 of that function to the negative 1/2. Put the inside function back inside and multiply by the derivative of the inside by the chain rule. And then the derivative of 5 times natural log of t is 5 times 1 over t. And you can simplify this if you want to. It's not necessary, but you can. So that's r prime of t. This curve is not smooth if there is a t value for which this is 0 and this is 0 and this is 0 at the same time. Now that one's always 0 on the domain. So that's not really helping us. But notice that 5 over t, that's never going to be 0. There's nothing I can plug in for t over here that will give me a 0. Can't plug in t equals 0. Dividing by 0 is not allowed. Plug in a positive value for t, I'm going to get a fraction. It's not going to be 0. Negative value for t, it would be a fraction, also not 0. And actually, I'm restricted to these t's in the domain, so no matter what t is in this domain, that's not going to be 0. So I'll just say I'm going to focus on that one. You could focus on this one if you wanted to. Since z prime of t equals 5 over t, and that is not equal to 0 for any t in the reals, r of t is smooth on its domain. Because I can't get this to be 0, 0, 0. There's not a way. Okay, so it looks like we're just going to do V8 on this video because I'm explaining everything in a lot of detail. Of course, if it's going too slow for you, you can always watch this a double time on YouTube, right? Okay. The last part of this problem is asking you to evaluate limits. The limits of r of t as t approaches 9 from the left, as t approaches 1, as t approaches 0 from the left, and as t approaches 4. So I'm just going to write this down. So the limit as t approaches 9 from the left of this function. So I've got 3 times t minus 4 over t minus 4, and the square root of 9 minus t, and 5 natural log of t. Now, if the limit as t approaches 9 of all 3 of these functions, as t approaches 9 from the left, if the limit of all 3 of these functions exists as t approaches 9, then this limit is equal to this limit. You just take the limit of each of the components one by one. Now these are just basic functions. It's a rational function. That's a composition of functions involving a linear function and a root function. I've got a multiple of a logarithmic function. All those functions that we've studied in previous classes are continuous on their domains. So if you can plug in t equals 9, or not necessarily 9, but something slightly less than 9, and this is well defined, or if you can plug in something slightly less than 9 and get closer and closer and closer to 9, and then you can plug in 9 to the functions, and that's well defined. That's the answer. That's the limit. It turns out all 3 of these functions are continuous at 9. Now I've got the limit of this over this. I've got a t minus 4 over itself. Those are the same. Anything divided by itself is 1, so those are gone. The limit as t approaches 9 of 3 is the same as the limit as t approaches 9 of this function, because we don't care what happens to this. We're going to have a problem at t equals 4 here, because we'll have 0 over 0. But t doesn't equal 4. T is something close to 9. It's slightly less than 9. So this is just a number divided by itself, so we get 1. So the limit as t approaches 9 of 3 is the limit of this function, and that's just 3. Now careful here. question is, can I substitute in t equals 9 to this? Well, sure, 9 minus 9 is 0, square root of 0 is 0. But be careful. Can I substitute in a t value to the left of 9? So like 8.99. Is this well defined at 8.99? I hope you said yes, because 9 minus 8.99 is going to be 0.01. It's a square root of a tiny positive number. A square root of a tiny positive number is even smaller. As t approaches 9 from the left, this is a tiny positive number. Square root of a tiny positive number is a tiny positive number. So as t approaches 9, we just get square root of 9 minus 9. It's continuous there to the left of 9, and that just reduces to 0. And logs are continuous on their domains. I can plug in 9 to that. If I want a decimal approximation, I can get out my calculator, but I don't need it. So that's my answer. Now I want to add one little restriction on this. This is equal to this, provided those limits exist. And those limits did exist, so we got the value of that limit. Okay. Now let's do the same thing for this. I have the limit as t approaches 1 of r of t. That's the same as the limit as t approaches 1 of x of t times I hat plus the limit as t approaches 1 of y of t times j hat plus the limit as t approaches 1 of z of t. And that's continuous at 1, and that's continuous at 1, and that's continuous at 1. How do I know? Because I can plug in 1 to all of those, and I get out an answer that makes sense. So this is equal to this, again, provided those limits exist. We're making an assumption when we write that equals sign. We're saying this equals this, and these exist. Or if these exist, they're equal. And the t minus 4 is still reduced. So the limit as t approaches 1 of 3 is 3. The limit as t approaches 1 of that square root is square root of 9 minus 1. Limit as t approaches 1 of this is 5 natural log of 1. Natural log of 1 is 0. So I've got 3, square root of 8, and 0. And square root of 8 is the same as 2 times the square root of 2. All right. So those limits all exist because the functions were continuous there. Okay, now this is a little tricky. T is approaching 0 from the left. You might already know the answer. This limit does not exist. How do you know? A couple of ways. This is continuous at 0. This is continuous at 0. That one we're going to have a problem. I can't take natural log of 0. That might be one way of thinking about it. Another way of thinking about it is, remember, if we're approaching 0 from the left, that's a tiny negative number we're plugging in. So I'm plugging in negative 0.1, negative 0.1, negative 0.001, negative 0.0001. And these are tiny, tiny negative numbers. I can't take the log of a negative number, and I can't take the log of 0. So this limit does not exist because the limit of z of t does not exist. Now if you did not know that, if you didn't think of that in advance, you could write the limit of this is equal to the limit of the x component as t approaches 0 from the left, limit of the y component as t approaches 0 from the left, and the limit of the z component as t approaches 0 from the left, but that last limit doesn't exist. So I'm going to write that down because that's probably what most of you did. But know that this is actually not true unless those limits exist. And it turns out that they don't all exist. Now you might have said to yourself, I already knew that that limit didn't exist because t less than 0 is not in the domain. Look what we did over here. We said you can't plug in something less than 0 because it doesn't work for z of t, right? So you might already know this, but if you didn't know that, you probably did this. And this is true provided these limits exist. And then we notice that component's limit does not exist. So we'll say, since z of t is undefined for negative t values, t less than 0, the limit as t approaches 0 from the left of z of t does not exist. And if that limit does not exist, that means that limit does not exist. And if you wrote, since natural log of 0 is undefined, the limit does not exist, that will work as well. But I think more precisely, we can't take the limit as t approaches 0 from the left, because that's going to be, that function doesn't even exist there. Okay, so now we're going to take the limit as t approaches 4 of r of t. And this, I noticed from your work, this really got some of you. This is equal to the limit as t approaches 4 of x of t times I hat plus the limit as t approaches 4 of y of t times j hat plus the limit as t approaches 4 of z of t times k hat. But some of you made a mistake. Now notice when I plug in t equals 4 to this, I get 0 over 0. That does not mean that the limit does not exist. From back in Calculus 1, if we had a 0 over 0 limit, what we would typically do is we'd say, okay, there might be a hole in the graph there. Let's see. If we can, we're going to factor and reduce. This one's already been factored for you. So you get rid of the t minus 4 factor. That gets rid of the 0 over 0 problem. Since we're taking the limit as t approaches 4, t is not equal to 4, so this isn't 0 over 0. It's just getting very close to 0 over 0. But as it gets very close to 0 over 0, this is just a number divided by itself, which is 1. So the limit of this guy is just 3. And that one is continuous at 4, so I just plug in 4. And that function is also continuous at 4, so I just substitute in 4. So I get this. Now, if you decide to reassess over this topic, it's not going to be exactly the same, but it will cover the same concepts. You'll be dealing with limits of vector-valued functions. You'll be finding the domain of a vector-valued function, figuring out where it's smooth. I might even give you one that's not smooth at a particular point, so be prepared for that. Also, you have to sketch vector-valued functions, the curves that they generate, or paths that they generate in 2D and in 3D. Now when you're doing the 3D ones, they're almost always these spiraling behaviors that are on some surface that we're familiar with. So make sure you've got all of your surfaces from the quadric surfaces section on your formula sheet, and make sure that you can see something like this and recognize that as an elliptic paraboloid that opens on the y-axis, on the positive y-axis. I know you guys can do it. I think all you have to do is prepare. Please come see me if you have any questions.